welcome back, and welcome back to the beautiful Gauss law, which relates the flux out from an enclosure to the total charge enclosed by the enclosure. Okay. Of course, we will take the help of what we know, that the electric field due to a single charge, and that we have taken as plus Q. And of course, whatever we know about Coulomb's law. Okay. So, let's have a spherical surface at whose center we have the charge plus Q. Radius is R, and the surface area of the total sphere, the surface area, is equal to capital S. Okay. Now, I can show it to you from Mr. Ali's ball that there is a surface over here, right? This is the surface delta S. Okay. And through this surface emerges out an electric field, okay, which I have shown as capital E. Okay. You can see that the direction of the capital E in this case and the direction of delta S there is the same. The angle theta between the two of them is equal to 0. Okay. So I write the electric flux, here in this case flux out, and I must make it clear to you that the electric flux is a scalar. The electric flux through an area element ds, delta S, okay, which I define as delta phi, is equal to E dot ds, vector E dot vector ds. And E is given by Coulomb's law. By now we remember it. Q upon 4 pi epsilon naught R square, of course, and the direction that is shown is R cap, which varies all over the surface of the ball that we have taken, the cube that we have, the spherical surface that we have taken, dot delta S. And everywhere they are both in the same direction, which I have written as R cap is equal to E cap, and therefore theta is equal to 0, and cos of 0 is equal to 1. We know this. Therefore this expression becomes equal to delta phi is equal to Q upon 4 pi epsilon naught R square into delta S. No vectors on this side, no vectors on that side. Okay. So if we want the total flux phi, then it will be sum of the flux for all delta S values. And in this particular case where I have taken this equal to S, okay, therefore it will become equal to the summation of all delta S is equal to S. So I will get Q upon 4 pi epsilon naught R square S, where S is equal to, for the spherical surface, 4 pi R square. Okay. Substitute this value over here, and 4 pi R square and 4 pi R square they cancel in the numerator and denominator, and I am left with Q upon epsilon naught. Okay. Q upon epsilon naught. So I write here now the sum of all these charges, positive, negative, etc. But we take it as positive because I have just shown you that out of this enclosure, okay, lines of field are going out. Okay, maybe not to the scale. So let me tell you the statement of the Gauss law is that the total flux through a closed surface enclosure is equal to 1 upon epsilon naught into total charge enclosed by this surface. Okay, inside. Well, now I have just drawn, this is not a circle, this is again a sphere, and this sphere is, like you can see that there is another ball over here inside. Okay, in Mr. Ali's this thing which he likes very much, the little kid, okay, more than 1.5 years old, always close it, and this is detachable, so this ball can be taken out. So let us suppose that this charge is inside this small spherical surface, okay, and that too we consider it to be at the center. So this kind of a situation there, and the flux out of this surface, bigger enclosure, will be the same as the flux out from here, which we have calculated in this case, and that turns out to be equal to Q upon epsilon naught. So we have taken the help of Coulomb's law to establish the Gauss law. Now, well, I'll just tell you, I'll detach myself from here and I will take you to the case of, suppose I have a big room here and you are sitting also in a room, and it has got certain inlets and certain outlets. If there is a single door, then from the same door you can come in and you can go out. Now suppose the volume of the enclosure is equal to V, okay, and the temperature be 0 degrees Celsius and the pressure be equal to 1 atmosphere. Listen very carefully. So we have STP situation in our room, standard temperature and pressure. The density will be fixed, the composition will be fixed. If the total number of moles is N, then the total number of molecules is also fixed according to Avogadro's law. Okay, so everything is fixed. And from the enclosure, there is a flux out and there is a flux in. Okay. Now let me say that there is a situation that the flux out is equal to flux in. So what do we infer? Okay, let's keep this question somewhere and put you another question, that the flux out is more than the flux in, and the situation is the same composition, same STP, everything the same, but what happens? That the outflux is less than the influx. So how can we think? If we put our heads together, then we have to agree that, well, besides the situation that you have described, there is a device within the confines of this room which is producing some air of the same composition and the same STP situation. So there has to be a source. If the flux out is in quantity is more, then that thing should be more. If the flux out is less, then that entity which we are talking about, something that has to be less. What if there is otherwise? That this is the production unit. Okay. If, now listen carefully, if it is otherwise, that is, the flux in is less. No. Oh. Flux out is less. Please correct. What is the other situation? There is something, flux in is more and the flux out is less. That means when we put our heads together, we say that look here, there is something which is absorbing the air. And if the difference is more between the flux in and flux out, then the absorber has to be stronger in character. More and more air should be absorbed. True? So what happens now? Let's take the question that we set aside. The first question, it means when the flux in is equal to the flux out, nothing of that kind, nothing of the kind of producer or the kind of absorber is present in the room. Okay? Now in our case, we are talking about electric flux. This is because of charges. So, in the first instance, for the first question, the total charge enclosed by, the sigma of the charge enclosed by the encloser is equal to 0. In the second instance, the total charge has to be positive, so that the flux out outweighs the flux in. And in the third case, the total charge has to be negative, which absorbs. That means the incoming lines of field are there more as compared to the outgoing lines of field. You understand that? So friends, I can say now, in our perspective, that the total flux out is proportional to sigma q, okay, which we can take, finally I have taken as equal to some q value. So, because there is a proportionality, a direct proportionality, so this is a system comprising two variables. Y is proportional to x. What happens to y is proportional to x? Y is equal to a constant times x. This we have done umpteen times, many a time we have done. Okay, y is equal to kx. So if I plot the flux out with the value of the charge that is enclosed, I get a straight line according to the system's approach. This y is proportional to x and y is equal to kx, which I gave to you the ideas time and again and again and again, but the first time in the initial lectures, where I said that the system which is isolated system, nothing comes in, nothing goes out, and there are variables, there are two variables, x and this, and k is not a function of x, k is not a function of y, is not a function of the defined variables of the system. So then k is a function of the system which has not been defined. Okay. So for this system, when I plot phi versus q, where phi is the flux, okay, I'm not giving you the units, etc., etc. So far I have not given you even the unit of the electric field, which is Newton per coulomb so far. But there is another unit of electric field which will come, which is volt per meter, and I will talk both the things at that time. So there is a straight line and there is a slope, and this slope is 1 upon epsilon naught. So if we have means of conducting an experiment where we can measure the value of the phi, okay, which of course not, and measure the value of the q which you are putting somewhere in this enclosure, because if you put so many charges and enclose it with a larger surface, then also the same thing will be true. In this case also the same thing will be true if the radius is increased or decreased, the enclosing radius is increased or decreased. Okay. So this is the way I have explained to you flux out and the dependence of the flux on that something. Here in this case is it charge, okay, and other cases can be there where the variable may be different. Gauss law applications may be taken in certain situations. So I have not derived the Gauss law from basic principles. We have derived it from the Coulomb's law in a very specific situation of a single charge. Using the Coulomb's law, we find that the flux is equal to 1 upon epsilon naught into q. Of course, in case it is not air or vacuum, then it is epsilon or epsilon naught. Epsilon naught, these things you can just make variations in your mind and think of that. So next, we talk about certain features of the Gauss law, okay, and probably I will wind up the lecture because it has been quite some time, and please listen to me very carefully again what I've said to you about this flux business. And once you get out of it, one thing I tell you, boys and girls, you are going to be happy, and when you are going to be happy, eat something which you like the best. So in the next frame I will tell you about certain features regarding our esteemed Gauss law. Gauss for very great grey matter possessor. I am to discuss with you the features of the Gauss law. A Gauss law which is stated just like this is left hand side is the flux and right hand side is the cumulative charge enclosed by closed surface or enclosure epsilon naught. Now some of the features, they have been enumerated like this. First, Gauss law is true for any closed surface, no matter what is the shape and what is the size. That surface is called Gaussian surface. Okay. The term Q on the right hand side, this is equal to the sum of all charges enclosed. Location inside is no matter. Doesn't matter where those charges are located. All charges can be positive and negative and this and that. Well, if the surface is chosen such that some charges are inside and some charges are outside, okay, the electric field whose flux appears there on the left hand side of the equation of Gauss law is due to all the charges both inside and outside the enclosing surface S. I'll elaborate on that. The term Q on the right hand side represents only charges inside S. Okay. So right now I am taking an enclosure, you can see, and I say that the net charge enclosed is equal to 0. This is an imaginary Gaussian surface. Gaussian surface. Okay. Now, what I show here is that there are some lines that are entering this volume and exiting out of it. If I just count the numbers, then as many lines which are entering here, how many? 4. They are fluxing in. And the same number, 1, 2, 3, 4, they are fluxing out. So flux in is equal to flux out, and therefore it comes to the first situation that I told you in the case of air inside a room at the STP, etc., that there is nothing that we can talk about. So there is nothing to collect the air or to release the air, as I said. So the charge inside has to be. And these naturally lines of field exist, but they must be from charges which are situated outside this enclosure. So this is what it means. Whatever surface we take in this relation where the phi is integrated over the entire surface, okay, this is actually integral phi integral d phi, okay, and it goes over the entire surface. Okay, hope you understand. Now I would like to wind up this, and in the next lecture I will take up the applications of Gauss law, the beauty shown to you. Okay. But right now I am going to show you how we can obtain the Coulomb's law from Gauss law. Okay. So in case of a spherical body like Mr. Ali's ball here, okay, so if the charge is put at the center of this spherical body, okay, then the electric field emanating from it and the surface, they are parallel to each other. That means they make an angle of 0 degrees. So cos of 0 degrees is 0 radians is equal to 1. So the result is that phi is equal to ES. You can write a few steps, EDS, this, that, and finally it will turn out to be EDS. Where S is the surface area of the sphere under consideration, sphere of radius r, and for a sphere the surface area of the sphere is 4 pi r square. So this becomes phi is equal to q upon epsilon naught. So from here I can write the equation E is equal to 1 upon 4 pi epsilon naught r square into q, right? And by the definition of electric field, and that the force is equal to electric field is equal to force divided by the test charge, and test charge in this case I have taken as equal to capital Q, right? So the force on capital Q due to the electric field over there turns out to be equal to 1 upon 4 pi epsilon naught q upon r square. Of course I can write this as 1 upon 4 pi epsilon naught q1 q2 upon r square. Khalas, beauty. So we can derive the Coulomb's law from the Gauss law and the Gauss law from Coulomb's law. Vice versa, we can do that. We can go forward towards the Gauss law, and we can go backward towards the Coulomb's law. I will take certain cases of distribution of charges, like line distribution, like a distribution over a surface of charge, like distribution over shells and or solid bodies, and we'll talk about all these things in the next lectures. But I insist that the Gauss law is the beauty. Of course, in choice of the Gaussian surface helps, because our mathematical tools are limited. Our knowledge of geometry off the cuff, off the hand is limited. So what helps us is what is known as another beauty of the nature. Another beauty of the nature is which exists, and geometrical patterns etc. are made and we know about them, and that is called symmetry properties. Okay. So yes, I take your leave, but for a long time I have been not telling you about what I write UVQA. No. UQVA. Please ask your questions, put up your queries. At the end of the lecture there is provision for that, and I can see that, and I have been answering those things. I will try to answer them. I don't say that I will satisfy you, but to my satisfaction I'll try to give an optimum answer to your minimum question. A good question is half ilm. So long, see you.